Hello everyone, this is Hussein Yusuf from Ethiopia. I'm Associate Researcher at Technology and Innovation Institute. Now I would like to present our conference paper, which is Autonomous RACH Resource Slicing for Heterogeneous IoT Device Communication via Deep Reinforcement Learning. Okay. Our work focus on the LTE 4G technology, which is important for dynamically sharing, allocating, and use of network resource. Basically, our work targeted to the random access channel resource optimization. This random access channel procedure is the first or the initial synchronization process between the device and the base station. The another terminology also currently the massive IoT device communications are exponentially increase in number throughout the world. Finally, the deep or the learning-based network resource allocation or utilization technique illustrated in this work. Okay, the main contribution of our work is the first one, RACH. In RACH procedure scenario, only six resource blocks are provided due to the radio resource rare and expensive. And also the second one is massive IoT communication devices also operate through these limited six resource blocks, even within different services, and have a variety of requirements. Those things result to the first one is affect the performance of human to human communication devices and the network becoming congestion, and also finally the massive IoT communication devices guarantees are not assured or maybe low. This is the motivation. Okay. And the significance of this paper is the first one is to extend RACH resource, extend this limited RACH resource, and the second one is manage a network current load, manage the network current load dynamically based on the coming request and also the available resources, Okay, and this is the objective of this work. The objective of this work, design a new RACH procedure, the first one, and also develop a model to control the network access problem through this random access procedure. This is to assure or provide a fair resource allocation with respect to guarantee of assuring the massive IoT communication device requirements. Okay, this is the sorry. Now, the main contribution of our work is the main one is we propose a dynamic RACH resource slicing, to extend those limited RACH resource, and also the second one is apply dynamic and multiple ACB mechanism techniques to regulate those massive IoT communication devices to manage the network the congestion problem. And also we design a new RACH procedure. We designed the new RACH procedure, maybe a little bit different from the conventional RACH procedure one. Okay, this is the overall operation of our work, the resource slicing and the device clustering, and also apply the dynamic allocation scheme, and then deploy the deep reinforcement learning with ACP and also RACH resource allocation techniques to the mock. Okay, this is the standard RACH resource procedure. It has four steps. After this, the device is getting the access. That means the device transit from the idle state to the connection state, maybe whether to send or receive data. Okay, this one is the new or the proposed RACH procedure. As you can see in the figure, we added two steps ahead. The two requests the slice as the isolated slices to the perspective from the perspective five classes of devices, and also getting that ACB factor parameter, and also the size fraction parameter. Also, the rest of steps are the same as in the previous conventional RACH procedure scenario. And this is the overall RACH virtualization. In RACH procedure, only one frame allocated at a time. That one frame has 10 subframes and 20 sub-slots. Those 20 slots, as you can see in the diagram, virtually allocated or mapped to the each five class of devices, as you can see in the right side of the diagram. This is the overall mapping or the overall virtualization diagram of the RACH resource. Okay, this one. This one is a deep reinforcement learning technique. And deep reinforcement learning, basically, or in general, the radio resource or network resource assigning, allocating, and managing, updating everything is very complicated, and the RACH resource allocation also face this kind of problem. So to tackle this kind of problem, deep reinforcement learning is a crucial role in this. Why? Because it is intelligent allocation strategy and learning, and also it is suitable for the online making decision techniques. Now this is the reinforcement learning formation seems like in this manner. The agent and the environment is contained the class of devices, five clustering devices, and also the inode. This is the environment, and the rest of parameters and simulations are mathematically expressed as like this. The state has five tuples: the number of successful devices from each class, the number of college devices from each class, then the time delay, and also the probability of RACH resource for each class, and also the probability of ACB factor to the each class to regulate whether to send or get the access. And the two important action parameters, PACP and also PRACHs. And finally, the reward is our objective of this work. The main probability access success calculated as like this, and our goal is to increase the number of successful devices within the minimum unwasted resources, and keeping the massive IoT communication device requirements. Okay, and this one is the overall deep reinforcement learning algorithms through those dynamic and multiple large resource slicing allocation techniques. Uh, this is the pre-trained or pre-defined paradigm of the deep reinforcement learning algorithm transformation. And the two very important actions are PSAP and PRACH to manage the sliced resource and also to regulate the number of in the rest of way of deployment of this framework is the same as the previous different works. And finally, we evaluate our work with respect to the following key performance indicators. The first one is access success, and the second one is access delay. And first, how we generate the devices as a node. You see within the same color, and we cluster the devices based on the different color. Then it's easy, don't worry. Okay, then this is the very important result and comparison part. The conventional RACH procedure within the conventional ACB mechanism versus the new or the developed the proposed algorithm. They are really based on ACB mechanism. As you can see in the figure on the left side, the conventional one, much resources are not allocated to any of the class of devices. It's too much waste of devices because of the conventional ACV mechanism without learning technique. And the second one is almost all the devices are fairly allocated. None of resources idle or unallocated. So that's nice. Okay, this is the second important parameter, access delay. To minimize the access delay, it is measured or indicate the satisfaction of the device. Utilization of the resource utilization also one of the main factor of the slight satisfaction. Okay, so as you can see in the figure, the left side, the estimated device, the estimated time delay. It is like the device can wait until they get the access, and the second one is based on those estimations. As you can see, the result rather than the delay tolerance devices, the rest of class of devices got the satisfaction more than in 90% almost. In detail, we can look on the paper in which that is a good result. Okay, to conclude that, in this paper, in this research work, two paradigms are applied. The first one is dynamic RACH resource slicing. This is to extend this limited resource, and the second one is multiple and dynamic ACV mechanisms. This is to adjust for to control or to regulate the network congestion problems. Those things are deployed on the deep reinforcement learning. Finally is assured the quality of service guarantee for the massive IoT communication devices. Thank you very much. This is our work. Okay, thank you.